Aditya, Sanskrit, lit. Sun, pronunciation, or Aditya L1 is a spacecraft whose mission is to study the Sun. It was conceptualized by the Advisory Committee for Space Research in January 2008. It has been designed and will be built in collaboration between Indian Space Research Organisation (ISRO) and various Indian research organizations, and will be launched by ISRO around 2019-2020. This will be the first Indian space mission to study the Sun, and also the first Indian mission to be placed at Lagrangian point L1, far away from the Earth, from where continuous solar observations are possible. Only NASA and ESA have successfully placed satellites at the L1 point as of date. An experimental budget of 3 crore Indian rupees has been allocated it for the financial year 2016-17. Overview. Aditya L1 is a solar mission. It was initially envisaged as a small, low-Earth orbiting satellite with a coronagraph to study the million-degree solar outer atmosphere, known as the solar corona. Subsequently, the scope of the mission has been enhanced and it is now planned to be a comprehensive solar and space environment observatory to be placed at the Lagrangian point L1. This enhanced mission, named Aditya L1, has recently been approved by the Government of India. A satellite placed in the halo orbit around the Lagrangian point L1 of the Sun-Earth system has the major advantage of continuously viewing the Sun without any occultation, eclipses. The Aditya L1 mission will be inserted in a halo orbit around the L1, which is about 1.5 million kilometers from the Earth. The satellite carries a total of 7 payloads with diverse objectives, including but not limited to the coronal heating problem, solar wind acceleration, coronal magnetometry, origin and monitoring of near-UV solar radiation, which drives Earth's upper atmospheric dynamics and global climate, coupling of the solar photosphere to chromosphere and corona, in situ characterizations of the space environment around Earth by measuring energetic particle fluxes and magnetic fields of the solar wind and solar magnetic storms that have adverse effects on space and ground-based technologies. The outer layers of the Sun, extending to thousands of kilometers above the disk photosphere, is termed as the corona. It has a temperature of more than 1,000,000 kelvins, which is much higher than the solar disk temperature of around 6,000 K. How the corona gets heated to such high temperatures is still an unanswered question in solar physics, with far-reaching implications for the heating of stellar atmospheres and magnetic reconnection or wave-induced plasma phenomena across the universe. Aditya L1 with additional experiments can now provide observations of Sun's photosphere, chromosphere and corona. In addition, particle payloads will study the particle flux emanating from the Sun and reaching the L1 orbit, and the magnetometer payload will measure the variation in magnetic field strength at the halo orbit around L1. These payloads have to be placed at a location with minimal influence from the Earth's magnetic field, which could not have been achieved at the low Earth orbit. Payloads. Visible emission line coronagraph, VELC. Coronagraph creates an artificial total solar eclipse in space by blocking the sunlight by an occulter. This telescope will have capabilities of spectral imaging of the corona in visible and infrared. The objectives are to study the diagnostic parameters of solar corona and dynamics and origin of coronal mass ejections, using 3 visible and 1 infrared channels. Magnetic field measurement of solar corona down to tens of Gauss. One wants to study the dynamical changes in the Sun, why the solar atmosphere is so hot and how the changes in the Sun can affect the interplanetary space and Earth's climate. The ejector and the particles coming from the Sun can affect the Earth's environment, called space weather. One need to predict that while studying the variability in the Sun. Pi Institute, Indian Institute of Astrophysics, IIA, Solar Ultraviolet Imaging Telescope, SUT. SUT will observe the Sun between 200 to 400 nanometers wavelength range, and it will provide full disk images of different layers of the solar atmosphere by making use of 11 filters. The Sun has never been observed from space in this wavelength range, the spacecraft being at the first Lagrangian point. SUT shall be observing the Sun 24/7, without any interruption. The payload is being developed under the leadership of Professor A.N. Ramaprakash and Professor Durgesh Tripathi at the Inter-University Centre for Astronomy and Astrophysics, IUCAA, Pune, in collaboration with ISRO and other institutes. One of the major unsolved issues in the field of astrophysics is that the upper atmosphere of the Sun is 1,000,000 degrees hot, whereas the lower atmosphere is just 6,000 degrees. In addition, we have not comprehended that how exactly the Sun's radiation affects the dynamics of the Earth's atmosphere on shorter as well as on longer time scale. There are multifold advantages of observing the Sun in this wavelength range. On one hand, we shall obtain near-simultaneous images of the different layers of the Sun's atmosphere, which shall let us study the ways in which the energy may be channeled and transferred from one layer to other. Using SUT observations, we shall also be able to shed light on the origin of energetic events occurring on the Sun's surface, such as flares and coronal mass ejections. On the other hand, the radiation from the Sun in this wavelength range governs the dynamics of the Earth's atmosphere. For example, formation and dissociation of ozone layers. The ozone layer is of particular importance as it blocks the UV radiation coming to the Earth and saving us from having skin cancer. Although solar radiation in this range is a very small fraction, approximately 8%, of the total solar radiation, it varies by about 60% over a solar cycle. The SUT observations will help us unravel the mystery of the cause of these variations. Pi Institute, Inter-University Centre for Astronomy and Astrophysics, IUCAA, Pune, Co-I Institutes, Indian Institute of Astrophysics, IIA, Centre of Excellence in Space Sciences, India, CESSI, IISER, Kolkata. Aditya Solar Wind Particle Experiment. Aspects. To study the variation of solar wind properties as well as its distribution and spectral characteristics. Pi Institute. Physical Research Laboratory. PRL. Plasma Analyzer Package for Aditya. PAPA. To understand the composition of solar wind and its energy distribution. Pi Institute. Space Physics Laboratory. SPL. VSSC. Solar Low Energy X-ray Spectrometer. SOLEX. To monitor the X-ray flares for studying the heating mechanism of the solar corona. Pi Institute. ISRO Satellite Center. ISAC. High Energy L1 Orbiting X-ray Spectrometer. HEL10S. To observe the dynamic events in the solar corona and provide an estimate of the energy used to accelerate the particles during the eruptive events. Pi Institutes. ISRO Satellite Center. ISAC. And Udaipur Solar Observatory. USO. PRL. Magnetometer. To measure the magnitude and nature of the interplanetary magnetic field. Pi Institute. Laboratory for Electro-Optic Systems. LEOS. And ISAC. Thus the enhanced Aditya L1 project will enable a comprehensive understanding of the dynamical processes of the Sun and address some of the outstanding problems in solar physics. Aditya L1 first Indian mission to study the Sun. Indian Space Research Organisation. Retrieved 1 June 2017.